Welcome to Chem 1A at Shasta College. This is Chapter 3, Composition of Substances in Solutions, Screencast number 3. Now next, how do we deal with compounds in terms of moles? And we've already started doing this. There'll be a little bit of repetition here, but good to get a fair amount of practice. And so let's keep considering the compound N₂O5 dinitrogen pentoxide. And let's start with the following. We have this compound, N₂O5. What do we know about 1 mole of it? Well, 1 mole of N₂O5, of course, consists of 6.022 times 10 to the 23rd N₂O5 molecules. And then each N₂O5 molecule contains 2 nitrogen atoms and 5 oxygen atoms, so we actually have 2 moles of nitrogen atoms and 5 moles of oxygen atoms in 1 mole of N₂O5 molecules. And then of course we also know that 1 mole of N₂O5 contains 2 moles of nitrogen, which is 2 times 14.01 grams, and it also contains 5 moles of oxygen, which is 5 times 16.00 grams, and that adds up to be 108.02 grams of N₂O5 in 1 mole. So same with compounds as it was with elements. There's a dual definition or a dual way of looking at mole. One is number of particles, but now we're dealing with molecules, not atoms. And the second is in terms of mass, and we have to add up all of the constituent elements in the appropriate amounts to get the mass of a mole of a compound. Now, how about if we have moles of a compound and we want to know how many grams there is of that? Well, we do the same thing as we did for mole to gram conversions for elements, except we have a compound. So we start with what we have or want, the thing we know, 5.338 moles of N₂O5. And then our conversion factor, if we want grams of N₂O5, we need to convert from moles into grams, and we know that 1 mole of N₂O5 is 108.02 grams, and so our conversion factor is set up like this, and when we do the math we get 576.6 grams of N₂O5 that is equal to 5.338 moles of N₂O5. What if we know the moles and we want the molecules? Well, we do the same thing we did with elements. We know the moles of N₂O5. We know that there is, in 1 mole of whatever we're talking about, in this case N₂O5, 6.022 times 10 to the 23rd particles of that thing. And in the case of a compound, the particles are molecules. So we set up our conversion factor to cancel out the units that we would like to convert from, to yield the units we would like to get, and doing the math gives us 3.215 times 10 to the 24th N₂O5 molecules. That's equal to 5.338 moles of N₂O5. The next question is how many oxygen atoms are there in 29.43 grams of dinitrogen pentoxide? And to answer this, let's start with what we have, which is 29.43 grams of N₂O5. And now we're going to want a conversion factor that converts from grams of N₂O5 into something that helps us proceed towards atoms. And of course, the most useful thing here is we know there are 108.02 grams of N₂O5 that is equal to 1 mole of N₂O5. So that conversion converts from grams of N₂O5 into moles of N₂O5. And then we're going to need to kind of string some conversions together here. So the next one is we know that each 1 mole of N₂O5 contains 6.022 times 10 to the 23rd N₂O5 molecules, and that converts moles of N₂O5 into molecules of N₂O5. And then last but certainly not least, we know that each one molecule of N₂O5 contains 5 oxygen atoms, and that converts N₂O5 molecules into oxygen atoms, and this gives us, when we do all of the math, 8.203 times 10 to the 23rd atoms of oxygen. And that is our final answer for that problem. Next, what is the mass percent of oxygen in N₂O5? And if we recall from before, mass percent of anything is going to be the mass of that thing. So we're going to want the mass of oxygen divided by the total mass. And then to get mass percent, we multiply by 100%. And so in this case, in N₂O5, probably the easiest thing to do is to say if we have 1 mole of N₂O5, we know that 1 mole of N₂O5 is 108.02 grams. And then we know that 1 mole of N₂O5 contains 5 moles of oxygen, so the total is 5 times 16 grams in 1 mole to give us the total mass of oxygen in this compound, in 1 mole of this compound, and then times 100%. And what we end up getting is 74.06% oxygen by mass in this compound. And then of course, if the question had asked for a percent of nitrogen, we'd do the same idea, but instead using nitrogen mass. And of course, we know that the answer is going to be about 26% because the total mass percent has to add up to 100. And if it's about 74% oxygen, then it's got to be about 26% nitrogen. Next, we're going to do an example where we have a hydrocarbon gas that we've analyzed and we've found its percent of carbon and percent of hydrogen by mass. And from this, we are to determine the formula of the compound, decide whether we've determined an empirical or molecular formula, and then determine what other information we would need to find the molecular formula if we've determined the empirical, or vice versa. So, let's do the first part, find the formula. And the key thing to note is if we have a compound, it has a constant composition, percent in this case of carbon and percent of hydrogen by mass. Now, we're not given the amount of compound that we have, but it sort of doesn't matter because whatever amount of compound we have, it's going to be 81.71% carbon by mass and 18.29% hydrogen by mass. And since percent is parts per 100, it's kind of the easiest way to deal with a problem like this if we just say, let's assume that we have 100 grams of our compound. And if we do, then 81.71% of 100 is 81.71 grams of carbon. And 18.29% out of 100 is 18.29 grams of hydrogen. And now, if we remember from previous problems, the formula for a compound is going to be the atom ratio, or the ion ratio, or the moles of atoms or ions ratio. And that means we need to convert to grams, from grams to moles, sorry. So there's 12.01 grams of carbon in 1 mole of carbon. And we can then convert our 81.71 grams of carbon into moles of carbon. Turns out it's 6.803 moles of carbon. And we can convert our moles of or grams of hydrogen into moles of hydrogen, because there's about 1.008 gram of hydrogen per 1 mole of hydrogen. That converts grams to moles, and we get about 18.14 moles of hydrogen. And then once we have the moles of the various substances, the various elements in our compound, then remember that the formula is going to be the ratio of atoms or moles, but as a whole number ratio. So what we want to do is take our moles and do a ratio. And it's easiest to do a ratio, in my opinion, with the biggest number, or in this case the bigger number, divided by the smaller number. And that mole ratio, moles of hydrogen to moles of carbon, turns out to be 2.667. And if you remember your fractions, 2.667 is about 2 2/3. And 2 2/3 is 8/3. And so essentially this ratio is an 8:3 ratio in terms of moles of hydrogen to moles of carbon. And that's a whole number ratio, moles of carbon to moles of hydrogen. That means that our compound is C3H8. Formula determined. Okay, next, which did we determine? Empirical formula or molecular formula? And what we found was C3H8. We found the smallest whole number ratio, and so we found an empirical formula, which is what a smallest whole number ratio is. Now, it's possible the empirical formula is also the molecular, but we don't know that for sure. And the information that would be needed to determine what the molecular formula is would be something like the molar mass, or a mass spectrum from a mass spectroscope. And the molar mass, well, notice that C3H8 is going to be 3 carbons, so 3 times 12 roughly, and then 8 hydrogens, so 8 times 1 roughly. So this is about 44 grams in 1 mole. And for the formula, 44 grams per mole, since the empirical formula has a mass of 44 grams per mole, if we find that the molar mass is 44 grams per mole, we know that that's the molecular formula. But if we found that the molar mass was, let's say, 88 grams per mole, then we'd know that the empirical formula is not the same as the molecular formula, and the molecular mass, or the molar mass of the compound, is twice the molar mass of the empirical formula. And so in that case, we'd conclude that the molecular formula was twice as big, or C6H16. But we don't know that for sure until we have molar mass data. So let's use this in an example where we have a particular compound that is 74.03% carbon, 8.70% hydrogen, and 17.2% nitrogen by mass, and we're supposed to find the empirical formula for this compound. By the way, this compound turns out to be nicotine, which of course is the real reason the dinosaurs became extinct. They just smoked too many cigarettes and all died of cancer. Well, maybe that's true, maybe that's not. But let's do the problem. And as we've seen before, best thing to do is to assume a 100-gram sample, which means the mass of carbon is about 74 grams, and we can convert that to moles. Mass of hydrogen is about 8.7 grams, and we can convert that to moles. And the mass of nitrogen is about 17 grams, and we can convert that to moles. Now notice we have moles of 3 different elements this time. And we again would like to find the simplest whole number ratio. That's what's going to give us the empirical formula. And the way we deal with this is if we have more than one compound, or sorry, more than 2 compounds, in this case 3, let's take the moles of each one. And usually the best thing to do is to divide all of the moles by the same number, which means the ratio stays the same. And it's most convenient usually to divide by the smallest number of moles, in this case 1.233. And when you do that, we get 4.999 moles of carbon to 7.00 moles of hydrogen to 1.000 moles of nitrogen, which is basically a 5 to 7 to 1 ratio. So C5H7N1 is the empirical formula for nicotine. Now, as seen before, we can determine molecular formulas if we know molar mass. And in this case, we are told that the molar mass of nicotine is 162.23 grams per mole. What's the molecular formula? Well, the empirical is C5H7N1. The molecular formula could therefore be that, or twice C5H7N1, which is C10H14N2, or 3 times C5H7N1, or C15H21N3, and so on. And what we know is that if we add up 5 carbons, 7 hydrogens, and 1 nitrogen, we get 81.12 grams per mole for the molar mass of the empirical formula. And if the molar mass of the actual substance is 162 grams per mole, which is about twice 81 grams per mole, then we know that that's the formula. If it had been 3 times as much, then we'd have the molecular formula being C15H21N3, and the molar mass would be 3 times 81.12, or 243.36. So we can conclude that the molecular formula is C10H14N2. There's what a molecule of nicotine actually looks like. You can count up the carbons, hydrogens, and nitrogens and see it is 10 carbons, 14 hydrogens, and 2 nitrogens. And in general, just remember, empirical formula is the relative numbers of atoms of each element in the compound, but smallest whole number ratio. And the molecular formula is the actual numbers. And here's another example, C6H12O6, molecular formula for glucose. All of these subscripts are divisible by 6, so the smallest whole number ratio is 1 carbon to 2 hydrogens to 1 oxygen. So that's the empirical formula, a 1 to 2 to 1 ratio, simpler than a 6 to 12 to 6 ratio. And that's it for the 3rd screencast.